Circuit analysis. Find the following values for this circuit, a little more complex than the previous ones. First, find R equivalent for R1 and R2, so it's going to step you right through the solution. Then find R equivalent for the parallel resistors here. Find the equivalent resistance for the circuit, current through the battery, voltage across R1 and R2, voltage across R3, voltage across R4, 5, and 6, and finally the current through each resistor. And just a reminder, circuits with multiple resistors are analyzed by combining the resistors into a single virtual meaning non-physical, it does not exist, resistor. The virtual or equivalent resistor has the same or equivalent resistance as the real physical resistors. And again, frequently we use these words as synonyms. The equivalent resistor, R equivalent, acts in the circuit just like the physical resistors. Part A, the equivalent resistance for these two resistors. They're in parallel, so we use the parallel equation here. We put in the numbers. We look for a common denominator, least common denominator, which would be 6 ohms. We add it together and we get 1 over R equivalent equals 5 over 6 ohms. So make sure you take the inverse or flip it at the end so you get the correct equivalent resistance, which is 6/5 ohm or 1.2 ohms. Here's a shortcut, or it may actually look a little longer than what we did, but if you don't like finding a least common denominator, let's do the algebra. So here's our equivalent resistance of two resistors in parallel. We cross multiply and then multiply the denominators and we get this phrase. Then we invert it. So here's our equation. This absolutely works for 2 resistors in parallel but won't work for 3. So we plug in our numbers and we see that we get the exact same equivalent resistance as if we had used the fraction method and finding a least common denominator. Now let's find the equivalent resistance for this group. And here we're going to use the least common denominator method because we didn't derive algebraically what the formula would be for 3 resistors in parallel. So the least common denominator is 10. Add everybody together. We get 10 ohms over 8 once we invert this guy here, which is 5 ohms over 4, and the equivalent resistance is 1.25 ohms. R equivalent for the circuit. So before we just redrew the circuits with the equivalent resistors, here's another method of doing it. Draw a diagonal line with the resistor on it through the resistors that you worked with, and then right above what the equivalent resistance there. So that's 1.2 ohms, and then the 3 parallel resistors we had 1.25 ohms. And it may be helpful, well it actually is very helpful, to label resistors with the found voltages and currents. So we're going to carry on with this process here because I've seen it done with the diagonal, I've seen it done with redrawing the circuit, whichever is more comfortable for you. Now find the equivalent resistance for the circuit. Well, here's our equivalent resistance A, so we're going to label this group A here, and this group here we've labeled B. You have the resistor in the middle, R3, and here's your equivalent resistance B. We could also have said that's our equivalent 4, 5, 6. So we're just changing notation here so you can see the different ways you can do this. So they're in series. However you label them, we add them together and we get an equivalent resistance of 10 ohms, which we then put right down here by the battery. We're in a position now to find the current through the battery because we have the voltage that was given. We found the equivalent resistance of the circuit as 10 ohms, so I is V over R. 12 volts over 10 ohms, we have 1.2 amps. And you can either write that down here, or like we've done here, just draw the current going around and round. Notice the full current goes through this resistance. The current splits here, and also splits here, but always recombines to get back to the total current of 1.2 amps. Now we need the voltage across R1 and R2. They are in parallel, so the voltage across each one of them is the same. They were replaced by the equivalent resistance R equivalent A, which acts just like the parallel combination. The voltage across R equivalent A will be the same as the voltage across R1 and R2. Now we're ready to use Ohm's law, where we have the equivalent resistance, and we also have the current coming through the equivalent resistance, and that current is just this guy right here. So the voltage across the combination of the two resistors is equal to the voltage across either one of them, and that will equal I coming out of the battery times the equivalent resistance, right? This I right here and this equivalent resistance here. So the voltage drop across both of the resistors will be 1.44 volts, and that's highlighted right here in the red box. Voltage across R3. This is a little more straightforward because look at this. We already have the current going through R3 and the resistance of R3. So V is equal to IR. Here's the current, here's the resistance, and we get 9.06 volts. Voltage across R4, R5, and R6. Once again, we can use Ohm's law where the current through the equivalent resistance, this one right here, 1.25 ohms, is equal to the current coming out of the voltage source, 1.2 amps. So the voltage across the equivalent resistance will equal the voltage across each of the individual resistors, and that is equal to the current coming out of the battery times R equivalent. So we put that in. 1.2 amps is the current. Right, this current here, it all goes through the equivalent resistance. See, that's where this diagonal would be helpful. Some people like doing that. I actually don't, but I've seen it done. The equivalent resistance is 1.25 ohms, and we find the voltage drop is 1.5 volts. A good way to check whether the voltage drops calculated is correct is to verify that they equal the voltage supplied by the battery. So we've highlighted them here. We have 1.44, 9.06, 1.5. We add them together, and yes, we get a total voltage of 12 volts, so it looks good. Or perhaps you could find a better way to do this. We knew this voltage, that's the battery. We found 1.44. We found 9.06. We didn't even have to use Ohm's law to find this voltage drop, right? Just add these together and subtract them from 12. But it's also good to use Ohm's law just for good practice and to make sure we're doing everything right. Because if we calculated the voltage drop here and find out that the three voltages didn't equal 12, then there'd be a mistake either there or there. Now we need to find the currents through each resistor. So let's start over here with R1 and R2. Good place to start. The voltage drop for each resistor is 1.44 volts, right? We found that right here. We want to find the current through each resistor, so it's just I1 is V1 over R1, and I2 would be V2 over R2. We put in the numbers, calculate it. We find I1 is 0.72 and I2 is 0.48. You add them together and you get 1.2 amps, which is I. So that's very good. So that checks out. And notice that the larger current, I1, goes through the smaller resistance, which also makes sense. The current through R3, wow, we found that way in the beginning. It's 1.2 amps, right? The current that comes from the battery, all of it goes through R3. So that's 1.2 amps. And finally, the current through resistors 4, 5, and 6. We know the voltage across each one of them. They're in parallel, so they're all the same. So you solve each one individually. I4 is 0.15 amp. I5 is 0.75 amp. Well, we're not quite up to 1.2 yet, are we? It's because we didn't do R6. That will be on the next slide. And here is our I6. V6 over R6, and we get 0.3 amps. And when you add the three currents from these three resistors, they correctly add up to 1.2 amps.